Okay, it's Thursday night. I've mustered up the energy to do this lesson. Yes. Okay. So this is curve sketching. So this is going to involve everything we've learned so far in calculus and also algebra. Okay, the steps I do today are the steps you need to do on your curve sketching project. Step by step. Everything I do is what you must do. So follow along. I'm only going to do one problem. It's probably going to take 45 minutes to an hour. Follow along, right? So guidelines for curve sketching. Step A, purely algebraic. Find the domain and the X and Y intercepts. That's it. Step B, symmetry. Is the function even, odd, or periodic? When I say periodic, that's if you come across a trig function. For these ones, I think I'll be nice and we'll only get rational functions, which are still not nice, but it's nice, okay? So if you remember what being even and odd means, even means you plug in negative x, you get the original function back. Odd means when you plug in negative x, you get the original function back, but all the signs have changed. C, find asymptotes. You will use limits to find horizontal and vertical asymptotes. All right. Step D and E is what we've learned so far, I think, in 4.1 and 4.3. We will look for intervals of increase and decrease and then max and minimums. Well, remember to find max and mins, you take the first derivative. You set it equal to 0. You solve for x. You make a sign chart. You pick test numbers. Then whether you increase or decrease will show you that we'll find your max and mins. Then F says concavity and inflection points. We've done that already. Second derivative. Set it equal to 0. Solve for x. Make a sign chart. Find points of inflection. Then take all this information and sketch the graph. Here we go. All right, domain and intercepts is first. Here we go. Example 1. Sketch the curve. Y equals 2x squared over x squared minus 1. So step 1. Let's look for domain first. Since this is a rational function, domain comes from the denominator. So I take x squared minus 1, and I set it equal to 0. I solve for x. X squared equals 1. Therefore, x equals plus or minus 1. But that can't happen because it makes the denominator 0. So there's my domain. If you want to put it in interval notation, that's fine as well. You don't have to. Interval notation would be negative infinity to negative 1, union negative 1 to 1, union 1 to infinity. Okay. Next is X-Intercepts. For our X-Intercepts, we will let y equal 0. Okay. So I take the function 2x squared over x squared minus 1. I set it equal to 0. And to make our life easier, X-intercepts only come from the numerator. So I will only take the numerator and set it equal to 0. So this means I get 2x squared equal to 0. X squared equals 0. And x equals 0. This means my x-intercept is 0, 0. And then I want my y-intercept. For my y-intercept, I let x equals 0. Okay? So that means I would get y equals 2 times 0 squared over 0 squared minus 1. Here I get y equals 0 over negative 1, which is 0. So my y-intercept is also 0, 0. Let me put those in another color so I know what we have. X-intercept, y-intercept. Okay, there you go. That part's done. 2 is we look for symmetry. So step 2. Symmetry. I will write this as f of negative x equal to, and now I will take negative x and plug it into the original function. 2x squared over x squared minus 1. So 2 times negative x squared over negative x squared minus 1. This gives me 2x squared over x squared minus 1. Did I get back the original function? Yes, I got back the original function. This means I got back f of x, which means we are even. Step 2 is done. Oh man, am I using my space correctly? A little bit. Okay. Now, step 3 is asymptotes. So maybe I can fit that here if I write smaller. So, step 3. We are first going to look for vertical asymptotes. And if you remember from algebra, vertical asymptotes happen at where your domain is undefined. So my vertical asymptotes are going to happen at 1 and negative 1. But we have to prove this by limits. So this means that, yes, I'll have vertical asymptotes at x equals negative 1 and x equals 1. But now we need to analyze those by limits. So we're going to start at x equals negative 1. We need to do a left side limit and a right side limit to prove that a vertical asymptote is there. So I will say the limit as x approaches negative 1 from the left of 2x squared over x squared minus 1. And I will also do one from the right. The limit as x approaches 1, negative 1, from the right of 2x squared over x squared minus 1. Okay, now here is where I would use the table feature in the calculator, or I would use my denominator trick where I plug in something close to -1 and I would get something like 2x squared over -0 would take me to -infinity. But if you don't like that trick, then yes, let's make an XY chart for these. So I'll make an XY chart for this limit. So I'll have my X and Y chart. Same thing down here. XY chart. Okay, so I'm typing that function in my calculator. 2x squared over x squared minus 1. And I want to approach -1 from the left. This means that the numbers are smaller than -1. So this means I want -1.01, -1.001, -1.0001. Let me see what I get. -1.01 gives me some really, let's see, 101.5. And then -1.001, -1.001 gives me 1001.5. And then -1.0001 gives me 10,001.5. So I can assume that as I get closer and closer to -1 from the left, these values are headed towards infinity. So this means that based on my XY chart, I get positive infinity. Now, let's look at the limit as -1 from the right. This means the numbers are bigger than -1. So the numbers I want are -0.99, -0.999, and -0.9999. 99999. Okay. -0.99 gives me -98.5. -0.999 gives me -998.5. And then -0.99999 gives me -9,998.5. So from those values, I can see that these are headed towards -infinity. Therefore, from my XY chart, we are headed towards -infinity. So what this means is that when x is at -1, so let me draw a graph real fast to represent this. So here it is. So when x is at -1, as we approach -1 from the left, one tail is headed towards infinity. As you approach -1 from the right, one tail is headed towards -infinity. This verifies by limits that there is a vertical asymptote at -1. So, put it together. This means vertical asymptote at x equals -1. Okay, now let's do it at the other x value where we don't exist. The other x value is +1. So let's do it again. Where could I start? Sorry, I wrote way too big the first time. Okay. So let's do it again. I'll just do it here. I just have to be really small. Okay. So at x equals 1, you get the limit as x approaches 1 from the left of 2x squared over x squared minus 1, and the limit as x approaches 1 from the right of 2x squared over x squared minus 1. Okay. Once again, XY charts. And this one is for numbers to the left of 1. So this means I'll want 0.99, 0.999, 0.999. So 0.99 gives me -98. 0.999 gives me -998. And then 0.9999 gives me -9,998. So again, just like the above, these values, as I get closer and closer to 1 from the left, are headed towards -infinity. So we get -infinity. All right. And then XY chart for numbers to the right of 1. 1.01, 1.001, 1.0001. Pick more numbers if you don't believe it. Add more zeros in there, right? So if I do 1.01, I get 101.5. So 101, then 1.001, 1001, and then this would be 10,001. So the more zeros I add, the more this number increases towards where? Towards infinity. So this limit is also infinity. Okay. And what that means is, I'll show it by the graph again. For x equals 1, yes, we know there's a vertical asymptote, but we have to prove it by limits, is that as we approach 1 from the left, one tail is headed towards -infinity. As we approach 1 from the right, another tail is headed towards infinity. Thus, proving by limits, we have a vertical asymptote at x equals 1. And yes, this is the process. You must do this. vertical asymptote at x equals 1. All right. Perfect. Well, that was just a vertical asymptote. We still have to find the horizontal asymptote. And I'm running out of room. It's okay. So, next is the horizontal asymptote. So remember, to find horizontal asymptotes, we look at limits at infinity. So I would say the limit as x approached positive or negative infinity of 2x squared over x squared minus 1. Well, no matter what for this one, if I plug in infinity or I plug in negative infinity, I'm going to get infinity over infinity, which is what form? Indeterminate, which means you get to use, or you get to take this limit to the hospital. So you get to use L'Hopital's on this. So if I L'Hopital's this, then I would get the limit as x approach positive or negative infinity. And the reason I write positive or negative infinity, because it doesn't matter if I approach positive infinity, it doesn't matter if I approach negative infinity, I'm gonna get the same asymptote. So that's why I'm including it both. So if I do L'Hopital's on this, I get 4x over 2x, which then reduces to 2. And guess what the limit of 2 is at infinity? It is just 2. So, with that being said, my horizontal asymptote is at y equals 2. There you go. Also, another way to prove this limit would be to use the power trick. Because let's say you couldn't use L'Hopital's. Let's say that it was undefined and you couldn't do it. Then you could power trick it and say the limit as x approach positive or negative infinity of 2x squared over x squared over x squared over x squared minus 1 over x squared would become the limit as x approach positive or negative infinity of 2 over 1 minus 1 over x squared. And as the limit goes to infinity or negative infinity, guess where 1 over x squared is going? 0. So this would just become 2. So remember that. If you can't use L'Hopital's, then try and power trick it. Okay. Either way, we get the same answer. But remember, in order to use L'Hopital's, it must be indeterminate. Okay? It's got to be indeterminate. Okay. Step C or 3 is done. Next, I'm going to put steps D and E together because, again, we're looking for max and mins, so D and E is that step together. It's find the derivative, set it equal to 0, solve for x, make a sign chart, find max and mins. So we're putting those together. So I'm going to stay steps 4 and 5 together. All right. Time to write small. So actually, let me make a barrier for myself. I cannot cross this line. On the left side, I'll have the first derivative. On the right side, I'll have the second derivative. So there we go. How's that? Look at that. Beautiful. Okay. Okay. Step 4 and 5. We're going to look for max and minimums. So let's take the derivative. The function is y equals 2x squared over x squared minus 1, right? Maybe make sure that's true. Okay. So now we will quotient rule this. So I get f is 2x squared. G is x squared minus 1. F prime is 4x. G prime is 2x. This means that y prime is going to be f prime g 4x times x squared minus 1 minus g prime f 2x times 2x squared is 4x cubed over x squared minus 1 squared. Okay. Cleanup time. Y prime is equal to 4x cubed minus 4x minus 4x cubed over x squared minus 1 squared. My 4x cubes cancel. And I'm left with y prime is equal to negative 4x over x squared minus 1 squared. There's the first derivative. Now, what do we do with that? We set it equal to 0. So, over here, y prime equals 0. I take negative 4x, put it over x squared minus 1 squared, set equal to 0. And remember, since this is rational, we get critical numbers from the numerator and we get critical numbers from the denominator. So let me do that here. So I'll say numerator, and that gives me negative 4x equals 0. Therefore, x equals 0. Denominator, that gives me x squared minus 1 equal to 0. Therefore, x would equal plus or minus 1. These are my what? Critical numbers. Okay, still working the left side. Now we make a sign chart. And I'll plot my critical numbers. -1, 0, 1. All right. And then intervals. Test numbers. X equals -2, x equals -0.5. X is 0.5. And then x is 2. Remember that this is a sign chart for the first derivative, so we plug these into the first derivative. Don't mess up a sign or you'll be ruined. Okay, I'm gonna plug in my derivative into my calculator, make this a lot easier. -4x over x squared minus 1 squared. Then go back here. Remember, I don't care about the number, I only care about the sign. So -2, I get positive. -0.5, positive. -0.5, negative. 2, negative. So plus, plus, minus, minus. Let's check it out. So plus, plus, minus, minus means, let me see, that was -4x over that. So that'd be negative over, yep. So be positive over positive and then negative, yep. Okay, so plus, plus, minus, minus, this means increase, increase, decrease, decrease. Okay. So looking at the sign chart, we look for our critical numbers to find maximums or minimums. And the first one we want to look at is -1. Look at the signs. We increase and then increase. Since there was no sign change, -1 is nothing to us. Then we look at 0. We increase and then we decrease. This means 0 is a maximum, right? 0 is a max. So let's put that down here. X equals 0 is a max. Okay. And then let's look at 1. Decrease, decrease. Nothing. 1 is nothing to us. So the only number I get here is that 0 is a max. Okay? All right. So since 0 is a max, we want to find the exact location of the max. So we take this number and plug it into the original function. Okay? So I want to find that exact location. So I say f of 0, and I plug it into the original function. 2 times 0 squared over 0 squared minus 1, which just gives me 0 over -1, which is 0. So this means that my max exists at 0, 0. But there's my max. Okay. How'd I do on room? Perfect. Okay. So 4 and 5 is done. We found our max and min. Now we move on to the last step of finding concavity, which deals with the second derivative. So I have all that space on the right. Let me pause for a second. Okay, let's continue. And we are on the step F, step 6, finding concavity. So that deals with the second derivative. So I'll rewrite the first derivative here. Where is it? Right there. Let's see. All right. So first derivative is y prime equals -4x over x squared minus 1 squared. Okay. So now I know the room I have to work with. This will be quotient rule again to get to the second derivative. So f will be -4x. G will be x squared minus 1 squared. F prime is -4. G prime will use chain rule. 2 times x squared minus 1 times the derivative of the inside, 2x. Clean up. G prime becomes 4x times x squared minus 1. Okay. Perfect. Now, let's find the second derivative, which means y prime, y double prime would be f prime g, -4 times x squared minus 1 squared, minus g prime f, 4x times x squared minus 1 times -4x. So 4x times x squared minus 1 times -4x, all over x squared minus 1 squared squared. Okay. Definite cleanup. Y double prime equals -4 times x squared minus 1 squared plus 16x squared times x squared minus 1. So I just did this -4 times that -4, 16x squared, over x squared minus 1 to the 4th. Okay, clean up some more. Y double prime equal to, I'm going to factor now, a -4 and an x squared minus 1 out of the numerator, bracket for neatness. This will leave me with x squared minus 1 minus 4x squared. So is that over x squared minus 1 to the 4th. Okay, almost there. Y double prime is equal to negative 4 times x squared minus 1 times this x squared minus that negative 4x squared is negative 3x squared minus 1. Okay. Over x squared minus 1 to the 4th. Now, this x squared minus 1 and this x squared minus 1 to the 4th will reduce. So, gone, gone, that becomes a 3. So, we get our second derivative as y double prime of negative 4 times negative 3x squared minus 1 over x squared minus 1 cubed. Right? Negative 4 times negative 3x squared minus 1 over x squared minus 1 cubed. Making sure I did my algebra right. Don't want to mess up this far. And that derivative, negative 4. Okay, looks good, looks good. Okay, so now set the second derivative equal to 0. So negative 4 times negative 3x squared minus 1 over x squared minus 1 cubed equal to 0. And since it's a rational function equation, we will have something from the numerator. So negative 4 times negative 3x squared minus 1 equal to 0. Divide the 4 off. Negative 3x squared minus 1 equal to 0. And then and then negative 3x squared equals 1. And x squared equals negative 1/3. Cannot use these because we will get imaginary critical numbers. So numerator's done. Can't use those. Next is from the denominator. Take x squared minus 1, set it equal to 0. And again, x would equal plus or minus 1. And since these are from the second derivative, these are called inflection points. But remember, they are possible inflection points, because we don't know if concavity is going to change until we make a sign chart. Okay, looking good. So right here, sign chart time. Plot my only inflection points, my possible inflection points. -1 and 1. Then my intervals are from -infinity to -1, -1 to 1, and 1 to infinity. Then my test numbers are x equals -2, x equals 0, and x equals 2. This is a sign chart for the second derivative. So plug these into your second derivative. F double prime of -2, F double prime of 0, F double prime of 2. So I will now look at my second derivative and type that into my calculator. I need to turn my light on. Okay, -4 times -3x squared minus 1 over x squared minus 1 cubed. Okay. Ooh, you know what? No, we're good. Never mind. Never mind, we're good. Trust the process. Don't want to confuse myself. So that -4 stayed there, because G prime is that times that. Okay, no, we're good. We're good. I promise. Okay. All right. -2 gives me positive. 0 gives me negative. And 2 gives me positive. So plus minus plus for the second derivative. Plus minus plus. Look at the sign chart. Plus means concave up. Minus means concave down. Plus means concave up. So looking at this, we look at -1, and does concavity change? That answer is yes. At -1, you go concave up to concave down. So -1 is an inflection point. Okay, now back. Let's look at 1. We go concave down, and then we go concave up. So concavity changes, meaning 1 is an inflection point. Now, since these are inflection points, we need to find the point of inflection. So we take these and plug them into the original function, right? So now, type this into the original function, which I lost that a long time ago, right? Anybody know what's going to happen when I type these in? Can I actually plug in 1 and -1 to this function? Look at my domain. My domain says x cannot be 1 and -1. But we'll try it out anyways. So if I type in -1, my calculator says error. If I type in 1, my calculator says error. Why is that? That is because at 1 and -1, we have vertical asymptotes. This means that there are no points of inflection. All of that, huh? Let's hope that doesn't happen on the problem I give you. So this means no points of inflection. And that's because they are vertical asymptotes. That's because x +1 and -1 are vertical asymptotes. So much abbreviation today. All right. Okay, which means we can now graph. Woo! We made it, guys. We made it. After I created such a mess. Okay. So we're going to graph this from all the steps that we started with. We're starting with step 1. Step 1 says my domain is x equals +and -1, and my x and y intercepts are 0, 0. All right. Well, actually, I'm going to look at all the points to adjust the intervals on my graph. So I have 1, -1, 0, 0. If I go to my horizontal asymptote is at 2, so I have a y value at 2. If I go to my max, it's at 0, 0. And if I go to my points of inflection, I have none. So what I'm going to do is space this graph out. I'm going to make this 0, 1, 2, 3, 4, 5, -1, -2, whoop, -3, -4, -5. then 1, 2, 3, 4, 5. I don't think I have any negative y values. Okay. So again, going back to the first step, plot your x-intercept and y-intercept. So 0, 0. Look at that right there. Ooh, which one am I going to use? The galaxy one. Look at that. Okay. So 0, 0 right there. Maybe more in the middle. There we go. 0, 0. Okay. Then step 2, all it says, are we symmetric? That means we'll be symmetric about the y-axis. So that'll let us know at the end if our graph is correct. Now 3, plot your vertical asymptotes and your horizontal asymptotes. I have vertical asymptotes at x equals -1 and x equals 1. So I'll plot those. All right, I'll use this color. So and then at -1. Okay, and now, and now we used everything from step 1, step 2, still part of step 3. My horizontal asymptote is at 2. So I'll draw that. And then, now step 1, 2, and 3 are done. Now we go to step 4 and 5. And the only thing I plot here is the only point I found, which is the max, which happens to be plotted already at 0, 0. There it is right there, which means step 4 and 5 are done. Then move over to step 6. And the only thing I want to plot from step 6 is my points of inflection, but I have none. Well, we're almost done. Whether I have points of inflection or not, we still finalize this graph by using the second derivative sign chart for concavity. This is why concavity is important. So what this sign chart says is that from -infinity to 1 to -1, I am concave up. So from -infinity to 1, I am concave up. So this is what it looks like. There it is. That's concave up. I'll write it in for you. Concave up from -infinity to -1. And then this says that from -1 to 1, we are concave down. So from -1 to 1, we are concave down, which means that this is what we look like. That whole part is concave down. And then from the rest of the concavity sign chart, from 1 to infinity, we are concave up. And again, this is concave up on 1 to infinity. Done. I don't even want to know how much time I spent. on one problem. This is why I only do one problem. And there it is. Okay. So just like I said, everything verifies this graph. We can even look at my limits to verify it. We said at -1, from the left side, the graph will go to infinity, and will go to negative infinity on the right side. Is that what my vertical asymptote says at -1? Yes. Infinity, negative infinity. Just like the graph shows. Infinity, negative infinity. Same thing at 1. Negative infinity, infinity. Proven by limits. So this is everything you need to do for your project. Step by step, maybe neater. Make some space. Don't make it all crunched up like I did. That's my bad. But these are the exact steps you need to follow. So I will probably be sending your projects out to you separately shortly, or well, not shortly, soon. You can at least enjoy the weekend, maybe. Okay, guys, that is it. That is curve sketching. No mas. I'm not doing any more of these. These are some of the problems I will assign to you for your project. So, but you will handle them in the same fashion as I handled this one today. That is all.